So we are dealing with a very difficult problem here because, as we well know, there is nothing more unpredictable than the weather. So why does this happen is because we all know the example of a butterfly effect that is very correlated to what happens in our atmosphere, so to speak. So every small change may lead to very huge impacts over time. And this is exactly what we are trying to cope with: the insecurity, the unpredictability of what can happen if we alter just one small parameter in the whole context. Also, we need to envision our atmosphere as a fluid environment, as so to speak, two fluids. We have air, we have water inside of the air, and all these convections between air and water, and so on. And this usually leads to some very chaotic behavior. Like, I think that we have all experienced turbulence in flight and so on. So from a mathematical point of view, coping with chaos is very challenging. And we've yet to have very practical solutions to modeling fluids, and especially turbulent behavior and chaotic behavior in fluids. There is research conducted in this area, but we're still far from having practical usages for it. So our idea was to see if we can employ machine learning techniques and deep learning techniques into this problem, the problem of predictability in the temporal context of weather, in the broader sense. Of course, our research in this project deals with a rather smaller sub-context, and this is the context of nowcasting. Okay, because the context of nowcasting brings more to the table, and we can see, I mean, I don't know, maybe if we weren't convinced a couple of years ago that this is actually something that concerns everybody, now we are more convinced than ever. Only a week ago or 2 weeks ago, Germany was facing a tornado out of nowhere, right? I'm sure most of you have heard of this. There was a huge tempest which caused some very devastating tornadoes in a temperate area, right? Which is somehow peculiar, if you ask me. But clearly this gives our research more of a practical purpose. So I think we are on the right track. I mean, if we manage to obtain actual software that can be employed, this can be very meaningful to the whole European community, so to speak, because whether we like it or not, we are actually trying to solve real problems like hailstorms, very violent summer storms of shorter periods. So I'm more and more convinced that we are doing this research at the best of times, because humanity is in dire need of solutions for these problems. So the only problem in our respect was to see if deep learning and machine learning may help in solving this problem of foreseeing the evolution of weather on a smaller scale, right? In a nowcasting context. Because if I were to be truthful, I would say that deep down in my heart, I would consider mathematical models more accurate in this. Like, if we try to model the atmosphere with equations and coping with chaos and randomness, I don't know, in my soul, I think that we would be more successful than with deep learning, although I'm a huge fan of deep learning. Also, the results that we will see at the end, that the results that we obtained are very encouraging, at least from an incipient point of view. And with some modifications and tweaking, I think that the performances obtained by our models can be, in a year or 2 years' time, severely improved. So what am I presenting today is an incipient model that can clearly be improved, and it can surely, it will with this the later improvements increase the already I would say performance accuracy that it shows. So first of all, in machine learning and deep learning, we base everything on the data, and we need to thank the Norwegian part for the quality of the data, which is it's high quality. It clogged our RAMs, so to speak, from the beginning. So finally, we have a problem in which we don't have scarce data. Okay, that is not a problem. The other problem was how to cope with the huge amount of data that was given to us, but that's not actually a problem in deep learning context. So our data was the satellite imagery from the Meteo satellite covering Europe and Africa. We received meteorological products, in our case, in form of a convection RGB, usually focused on the icy clouds that generate hailstorms and more violent storms. And also, we only focused on the European region in our research. We will discuss a little bit later the scope of our investigation. First, we started on a broader scale, like on images of the whole northern hemisphere. But we asked ourselves some questions with regard to what we are trying to achieve, and we narrowed it down for a couple of investigations. So that is actually a question that I would like to keep for the end of the presentation. So once we established the inputs, now we had to consider what our best option of a deep learning model is, right? So we consider that we need to balance complexity and simplicity, and therefore we scouted our options, and we decided to use a ConvLSTM architecture. Basically, we have seen the ConvLSTM architecture working very well with, you can see here to the right, that's the dynamic mână-IST data set. This is a benchmark basic data set, but we consider that this behavior is somehow similar to what we are trying to pursue here, like to a dynamic, slightly chaotic, but also somehow governed by some sort of rule type of movement in time. So we need to deal with temporal data, so data that evolves in time, and also we need to balance chaos and order, so to speak. So we consider that since this ConvLSTM model works well on data sets just like dynamic mână-IST, maybe it will give good results on a similar context, which is the progression of weather over time. So this was our claim. Let's see if this works. And on the other hand, we kind of need a non-bloated learning mechanism, because the sheer volume of data, in my opinion, is quite considerable, and therefore the computation needs to be toned down. So we try to balance the complexity of our computation with the simplicity of the architecture. So what the ConvLSTM is we take a recurrent neural network that is usually used to learn regression in the temporal context, and also combine it, because at each time step we receive an image from the satellite, and we said previously that every 15 minutes we receive a new refreshed image from the satellite. Then we need to combine the temporal aspect of learning with the analysis of images. Therefore, we have an LSTM of convolutional networks that we try to employ into predicting, based on previous frames, one or several subsequent future frames. So the proposed architecture was, we tried several architectures, I think that the first one was more bloated with more layers, and in time we reached a saddle point in how many layers we should use, and this is kind of in a middle ground, right? It's not the most bloated and neither the skinniest architecture that we found. And we conducted a series of experiments. I will come back and give you the details on what we found in the process. But long story short, at the beginning, the problem was that the images that were obtained as a forecast were very similar to just the current image that was given. They didn't seem to have a generality. They seemed very similar to the image that was right before, and just that one. It didn't do anything with the images in front of it, and this wasn't a good sign. But on the other hand, this led to a discussion about the time step between two consecutive frames that we give as an input. Because if we look with our own eyes to the evolution from 15 minutes to 15 minutes of let's say the weather on Europe as a whole, we will not see much change or visible change or significant change as we would want. So maybe we can gallop over, we can skip a few frames and find the subsequent frames that are more dissimilar. And this way, we will know that the prediction that we will get can't depend only on the previous frame, because they would be more different. So we try to do that, and that is how we discovered that this wasn't learning very well at the beginning, which enabled us to simplify our architecture. And also in time, after a few tweakings, we managed to create a model that was actually using more than one previous frame to foresee the next one frame. So it was a little bit difficult to evaluate our model on a benchmark against the literature, and this would be a desiderate for us in the future. We are working on that, but having access to benchmarks that are used by the people at NASA or something, or in America or Google, that they have several researchers in this aspect, is more difficult than we could handle that right now. So what we wanted to see is how our model performs against other models used in other research papers from the literature on the same data set that we had. So we compared our model against a convolutional neural network, a baseline one, just a regular convolutional neural network, a UNet, and also a generative adversarial network, because actually we consider that also the GANs can be used to generate a next frame based on previous experiences. So we can see that our solution outperforms the others. However, the real test of the model would be on actual benchmarks against some industrial level approaches as well. However, based on the experiments that we have conducted so far, the progress was very visible. I mean, with respect to the evolution of the model itself, at the beginning, as I said, we had some problems that it was only learning from one frame, and now it is generalized to work with previous several other frames, which is I think it's a very consistent improvement. Also, we tried, and it showed good results. And this is a question that I would like to address, especially to the meteorological people involved here in the discussion, is that since we are trying to cater to the nowcasting needs, would it be a good idea to narrow down the region of focus for our experiments? Because now we started with the whole northern hemisphere and tried to foresee the images depicting weather evolution in the whole region. Then we kind of zoomed in, and this led, of course, to more diverse, a greater diversity between consecutive states. But the idea is that I would think that there is a saddle point here as well. I mean, how much would it be okay to zoom in in order to follow the purposes of nowcasting, not just weather forecasting, but what would be the scale of the region of interest with respect to nowcasting? Because in theory, nowcasting only focuses on a smaller surface of Earth, and in a couple of hours' time in the future. So if we receive 15 minutes worth of frames, that would mean that we can extend our model to foresee, let's say, 6 or 7 future frames to be predicted. But I think that it would be a good idea for us to focus on just a region of interest that is catering best to the needs of nowcasting. At least from our experiments, playing with the region of interest, like zooming in, helped. It helped. First, it helped for us to witness the differences between our prediction and the ground truth, our prediction and the previous frames, because when it was from an outside point of view, witnessing the whole northern hemisphere, the differences were so slight that us as humans, we couldn't perceive if our model was actually doing something creative in predicting the next frame or just based on the previous frame, and that's it. So this would be one question related to the opening of the region of interest. Another one is something that I would like to discuss about what happens after we provide the model, right? So we as data scientists, we give data to a learning model, we crunch the numbers, our computers crunch the numbers, and then we look at the numbers and check the error rates and so on. And if they're small, that means, and if the model learned well, we say that it performed admirably. However, now in this interdisciplinary context, we are not only looking for small error rates, right? We are also looking to provide a practical application to our model. And this is another discussion that I would like to begin here. How can we validate the results of our model from a meteorological point of view? Even if, so we encountered some situations in which the error rates were small, but meteorologists said that the depiction of what happens in the atmosphere is not it's not natural. Another context would be the opposite. Like you have huge rates and somehow the results look too good to be true. Huge rates of error. So I think that once we refine our models, so that computationally they are beyond the shadow of a doubt working, the next step would be to see what this means from the meteorological point of view. Because to me, it was very interesting to hear some of discussions about the dynamics of the result and it not being, it would not be in a natural fashion. That is fascinating to me because clearly that can happen. Like your model is just crunching numbers. It doesn't know that it's modeling the amount of water in the atmosphere and the way it should be doing. It should be moving in a realistic context. So as far as we know about this model of ConvLSTM applied on satellite imagery, we can say that the error rates are more than satisfactory at this level. And what we are trying to do, we are pleased with the performances, at least for now. However, we would like to know from discussions with the meteorological part, if this reflects also in the difference between the ground truth and what we have predicted and so on and so forth. So I'm looking forward to those discussions, especially after we further improve on our current models. So with this in mind, this is what we are trying to do from now on. First of all, we try to make more experiments, to conduct more experiments on various scales, regions of interest, and gaps between consecutive frames that we show to the network. So we can see for which combination of those it performs better, not necessarily from a mathematical point of view, but from the meteorological point of prediction.